All right. The first one here, this is the photoelectric effect. Okay. So that's the maximum kinetic energy of the electrons, right? This is the photon energy, right? So that's Planck's constant. That's the frequency, right? And then that's the work function. Now, typically we do these in electron volts. Okay. So for example, and I usually think of the equation this way, right? Photon energy in the best case scenario becomes work function, right? This is the energy needed to pull that electron off the surface of the metal, okay, plus kinetic energy, okay? And we measure the kinetic energy with voltage, right? Okay, so if an electron can fly through, say, 4 volts before it stops, it's got an energy of, say, 4 electron volts, right? Okay, so that just means that the stopping potential was 4 volts. It's an electron. It stopped at 4 volts, right? So we can measure this directly, right? Let's imagine that the work function is 3 electron volts, right? That means that the photon energy was 7 electron volts, right? Okay, so the work function is just a property of the material. They'll tell you that, or you can calculate that, right? This is the strange way that they write the equation, and there it is, right? I always think of it this way, though. Okay, so they just subtract the work function from that to get the maximum kinetic energy. Okay, I suppose they could give you a problem in joules, just go along with it, but typically photoelectric effect problems are done in volts, just because we measure the kinetic energy by using a reverse potential that slows the electrons down. And we know that if it can go through 4 volts, but it can't go through 4.0001 volts, that the energy is roughly 4 electron volts, right? Okay. And then the photon energy, you're going to use hc over lambda, okay, to find that. And then convert it to electron volts, or use the value of hc, right, where hc is 1.24 times 10 to the minus 6 electron volt meters, right? I mean, it is a timed test, so let me make sure I'm giving the right number. Yeah, there it is, right? And that's on page 4 of the data packet in the unit conversions section, right? So you can just slap that in there, divide by this. Don't forget to convert nanometers, 10 nanometers, 10 to the minus ninth, and you're set. So they love photoelectric effect problems. You've got, I don't know, 30% chance of seeing one on the test. Okay, this is the de Broglie wavelength, right? So we have light, which we thought was a wave, acting like particles and photons, right? This is one example of light acting like a particle, right? Is the photoelectric effect. Okay, and then de Broglie hypothesized that small particles could act like waves, and indeed they can, right? We have electron microscopes. We make images with electrons, which is cool, right? And so the de Broglie wavelength, the effective wavelength, is Planck's constant divided by the momentum, right? So ultimately it becomes Planck's constant over the mass of whatever it is times the velocity. Okay, yeah, the de Broglie wavelength. And of course, everything has a de Broglie wavelength, but the de Broglie wavelength of a baseball is 10 to the minus 34th meters, and so it doesn't exhibit wave properties because it can't interact with barriers or things that are, nothing is 10 to the minus 34th meters, right? Yeah, anyway. And then this is a new one to me. I guess you guys had to learn this. Okay. This is for Compton scattering, right? So you got a photon coming in, you've got an electron here, and then that photon goes off in some other direction like this, right? And there's some angle between the original path of the photon and that path. The weird thing about Compton scattering is not only does it bounce off like a particle, but the wavelength gets longer. Okay, that longer wavelength, remember, means less energy, right? Why does it longer? Well, because this guy is shooting off like this, right? Okay, and it's got some of the energy that this guy has. This guy's a shorter wavelength. So this is weird, right? You shine light on a metal, and the wavelengths that come off are longer, right? So this is not something that the wave theory would predict, right? Because that's the frequency changing. That's strange, right? Okay. And so how much does the wave change? Well, there it is, right? That's the change of it, right? Okay. And then this is Planck's constant, right? So 6.63 E minus 34, that's the speed of light, 3E8, right? And then the mass of the electron is 9.11 E minus 31. This angle is that angle right there. And so the biggest change in wavelength is if the photon comes in and then just comes straight back out, right? Okay, that's 180 degrees. Well, the cos of 180 is -1. 1 minus -1 is 2. Yeah, that's the biggest you can get, right? If that's possible. I haven't taught this ever. So anyway, but I do remember it. Anyway, I think that's all we have for the equations. All right.